Hello. In this demonstration, I will show how to run linear regression in PySpark. This is a follow-on to my demo of showing how to run linear regression in Python. So the idea is we've got here a scatter plot of data, and we're going to take an X value, say something along this area, average area income X-axis, and predict a Y value. So that's our job, and eventually we'll have more than one X value. We'll have a number of X's, if you will, number of dimensions to predict the Y. But first we'll start off with one variable regression. And with this simple idea, here's a number of points, and our objective of the linear regression is to fit a line that best goes through the points. And given our X values, we're trying to find appropriate Y values that fit along this line. So we're predicting Y's, we're given X's. This line is then defined by the coefficient for X, which is the slope, and the intercept where this line hits the Y-axis at X equals 0. So that's our task, and we have some tools that use ordinary least squares, which is a method to find this line. And here's a graph of how the line fits through that data. So this is how it's done in PySpark, which is slightly different than it's done in Python. In PySpark, all of the X's, all of the independent variables used to predict your dependent variable, your Y, have to be put into a single column. And the way to do that is to use this vector assembler. So we'll take multiple columns, and in this simple demo, I've just got one column, the average area income, and we pass it off to the vector assembler, which is going to take this one column and put it into another column called features. Eventually, though, we'll have multiple columns. And this feature column will have all of our features for our model. And we can then transform that input data, the U.S. housing data, using this this vector assembler. So we're going to take the input data and transform it using this vector assembler as specified. So the average area income will be transformed into a new feature column that's actually a dense vector. Okay, and then once we have that, that can be input to our linear regression model. All of the models in the Spark library, they take a feature column, one single column that contains within it our multiple features, our multiple columns in terms of Python, our multiple X's. And we have a column that we're going to predict, the labeled column called price, based on our features. And once we have this instantiation of this linear regression class called LR, then we can fit it, and it is fitted to the data that we transformed. So this data now is in a format, the assembled data is in a format that the linear regression model can deal with. Okay, once I've got that linear regression model fitted to the data, this fitted linear regression model, I can do things with it like print out the coefficient, intercept, and R-squared and all of that. So you can see here that my fit is 0.4, which is pretty low. So we would improve on that by adding some more columns to our regression. So eventually we'll do that, and that's shown here. We'll have a number of columns. In fact, we'll have all of our columns, but excepting the column we're going to predict, which is price, and a text column. And all of those columns will be used for a prediction, and our vector assembler is going to take all of those columns and put them in a feature column. And in this case, now I've got a pipeline because I'm going to do a number of steps, and it's going to be simpler rather than to manually code in PySpark these steps. I'm going to declare what I want to have happen. That is, I'm going to have a vector assembler that's going to work on these columns I've specified. It's going to be passed off to a standard scaler, which is going to work on the output of the vector assembler. And the output of the vector assembler is going to be some features, which is going to be input to my linear regression, which is then going to predict my price. So I've got 3 steps here in my pipeline. So this pipeline looks quite similar to the Python sklearn pipeline, which inspired the API here in PySpark. So once I have my pipeline object, then I can do the same sort of thing I would do in Python and also PySpark. That is, once I have one of these estimators, I can fit it. I'm going to fit it to my data. This case, I'm fitting it to my training data. And then once I have that fitted model, then I can pull out the linear regression part of that and print out information about it, the intercept, the summary, and so forth. Okay, so first is to use standard PySpark regression without a pipeline, and second is to show how to do it with the pipeline. So let's go to DataBricks and run a PySpark demo. Here I am in my notebook, and I'm going to run some PySpark regressions. I've grabbed some housing data, and once I've downloaded that, I'm going to read the data. It's going to be read into a Spark data frame. So this data frame is like a pandas data frame in Python, but it's a Spark data frame, distributed over the cluster. Okay, I can display information about the data frame, and in this case, I'm going to cast some of the names, cast some of the data to double, and change some of the names because they have spaces in it. So I'm just cleaning up the data a little bit, and eventually I get this Spark data frame called USA Housing. So once I have that, I can go ahead and do some regression with it. And the first one I'm going to do is just a simple one variable regression. So all these models in Spark need to have their data in a particular format. The format is one column where multiple columns of data are put into a single column. So as my input might have like 3 columns, then those 3 columns will be put into a dense vector and then placed into a single column. The way to do that is with using this vector assembler. So in regular Python, I might have 2 separate series here, an X series and a Y series. But in PySpark, I'm going to take all my X's and have it as input to this vector assembler, which is then going to convert it when I do my transformation into a new column of whatever name I choose, and the default name is features. So if I scroll down here a little bit, you can see that I've got this new feature column. So over here at the left is my original data frame and the columns I had. And at the right is my new column created by the vector assembler when I did the transformation. And if you look at it carefully, it's a dense vector of length 1. And that's because I only have one input column. Later on, when I have multiple input columns, you'll see that length will be more than 1. All right, so the models in Spark are going to take this single feature column and then work with it. So in order to prepare the data for my linear regression, I have to run the vector assembler or something else that's going to take multiple columns and put it into one feature column. Another transformation is our formula, which will do the same thing. All right, right now we're taking the vector assembler, taking as input this average area income, and output a new column called features. And the first step is I'm just declaring that that's what I want to have by creating an instance of the vector assembler. And the second step, I transform, which actually creates this assembled data. So now I've got this assembled data, which I have my features defined. Okay, once I have that, now I can go ahead and select my features and price. And this is really going to be the input for the linear regression. The features, and right now I just got one feature, one variable regression, and the price, which I'm going to predict. So I'm going to fit my model to this data here. So just to show you what it looks like, I'm going to go ahead and just use regular old Python. I'm going to use Seaborn to do a scatter plot of the pandas data frame, which I converted my Spark data frame to a pandas data frame using two pandas. And I took the X as the average area income and the Y is the price. And I just plotted out that information. That's all I did there, just to see what it looks like. Just a reminder what our task is. The idea is to find some sort of line that's going to go through the data. And linear regression is going to be define this line. So let's get to it. Let's make an instance of my linear regression from the PySpark ML library. And the way I'll do that is I'll say, linear regression. I'll give it some information. The labeled column will be price. And the feature column is features. That's my instance of my linear regression. So now that I have that object, I can go ahead and fit that to my data. I can't fit it to the original PySpark data frame. I have to fit it to the assembled data, which is a transformation using the vector assembler. And that's the one that has all of my X's in one column, in the feature column as a dense vector. So that's what the linear regression is assuming is in here. And sure enough, it works. So I've got my fitted model now. And once I have my fitted model, then I can go ahead and do predictions with it. So I can give it as input, say 18,000, and then it'll tell me what the housing price would be. So my model now predicts things. It predicts prices given inputs. And I can show you what those predictions are. So I can take my model that has been fitted, and now I transform the assembled data, and now I get to see all my prices, the original prices, and the predicted prices. And ideally, these are exactly the same. The R-squared would be 1, but of course, it's an imperfect prediction. I can also take those predictions. Here's my results. And I can select the price and prediction column as I showed above here and convert those to pandas. And then once I have that, I can do some nice plotting. In Seaborn, I can do an LM plot, for example. Now, if I had, a big data is in, billions or millions of rows, then I'd have to sample this. I can't convert, billions of rows to run in one computer. So I would sample the data and then convert it to pandas. But in case for this simple data set, I would go ahead and just convert it to pandas and plot it. I can also print out other information about this model that I have above. Remember, this is the fitted model, and LM is my fitted model, so that linear model. And I can print out information from it, the coefficients and so forth. Okay, so I can also show what the line looks like, and that's what I'm doing here. I'm using a line plot to go ahead and take the scatter plot and pull out from my coefficients. M is my X coefficient, B is my intercept here for linear model intercept, and I can produce a line here from this, and then I can use that to do my scatter plot over the data and then also plot out the line here, which is what I've done. So I'm just showing you can take from the linear model, get the actual equation and plot that equation over the scatter plot, just showing you what the result of the linear regression looks like. Okay, so now next up, let's, instead of just doing one variable, let's do multiple variable regression. So what do we want for our variables? So I'm going to take the housing columns and get rid of the one that I'm trying to predict, price. That would not be good to put as an independent and dependent variable. So I'm getting rid of price. And address is a string, and I can't really do anything with that. So I'm going to take the other columns, though, and that is this average area income and so forth, 2, 3, 4, 5. These 5 columns I'm going to take, and I'm going to use them to predict price. So I'm going to tell the vector assembler, take those 5 columns, that's the input, and I've just expanded that list of columns, and we're going to put it in the feature column, and it's actually done here in this second step. After declaring the vector assembler, I'm going to do the transformation of my housing data, and that produces this assembled data, which I've shown here. And if you look at the assembled data you look at the feature column, you can see that the length of the feature here is 5. And that's going to be the same length of these columns, 1, 2, 3, 4, 5. So that these 5 columns have now been put into this single feature column, and that's necessary in order to run all of the Spark learning models. Okay, so now I've got this feature column and it's ready to go for my my learning model. All right, so first though, I'll go ahead and take my data and I'll split it up into training and test data. And next I will create a linear regression, an instance of this class. I'll tell it that the column I'm trying to predict is price, and I'm going to use the input of features, which has been transformed from the original Spark data frame. Now it's in one single column. I've got a feature column. And once I have that, I can take that linear regression and produce a model based on the training data. So LM now is my fitted model. And once I have that fitted model, I can go ahead and print out all my stuff. I've got my equation, intercept, R squared. And once again, the R squared is a little bit better when you use more than one of your X's, more than one column of information. Okay, so that's a little bit better. I can also take that linear model and produce the prediction. So I'll take my test data to get the resulting predictions. I can select from that result just the price and prediction. That'll be my predicted values and the actual values of price. And once I have that, I can then use that. There's a regression evaluator that, given this predicted values, I can go ahead and take this evaluator and evaluate my results, and I'll get an R squared. So I tell the regression evaluator the predicted column is the one above, called prediction, and I will tell it that the labeled column is the price column in the metric. There's other metrics like root, mean squared, error, but here I want to do R squared, which is R2, and I'll print out the results of that by telling the evaluator to evaluate my data frame that includes these. It's a Spark data frame that includes the price, the actual price, and the predicted price. Okay, and if I want to graph it, I usually use regular stuff in Python for graphing. You can sample if you've got a lot of data. In this case, it's small enough. I just convert my predictions to a pandas data frame, and I'll do a plot of that data frame doing the price versus the prediction, actual versus the prediction. All right, so that's good. That's good. So let's now, though, let's do a pipeline. I would say this is the way to do it in PySpark, is because we always have to run that a vector assembler or something like that, and then a model. So we always have 2 steps in our pipeline, and typically we'll have more steps, especially if we're going to do natural language processing. We'll have many steps. So, all right, so we're going to use a pipeline, which is from Spark ML, and we'll go ahead and split up our data as we've done before. And in this case, I'm going to have a simple pipeline of 2 stages, the same I've shown above. I'm going to do assembler, followed by my linear regression model. And I didn't define these assembler and linear regression model. Remember, they're defined above. So if I scroll up, LR is going to be my linear regression model. It's going to take in features, and it's going to use price as the column it's going to use for prediction. And assembler is above, and the assembler has the input columns, and it outputs features. So I've already defined these above. I didn't redefine them below where I did my pipeline. Just note that the assembler is defined above and the linear regression is defined above. So I'm going to take the pipeline class and make an instance of it. And these are the stages. It's going to be 2 steps or stages, the assembler followed by the linear regression. Once I have that pipeline, now I can, that object can be fitted to my data. So I've got some training data. And the result of this is I've got a fitted pipeline or fitted model. And I can look at the stages in that fitted pipeline. So here are my stages. And you can see they should be the same ones I defined above, but they're instances of vector assembler and linear regression. So these are the models above, and now I've got them as stages in my fitted model. Okay, well, if I take the first of those, the second in the list, but labeled 1, in Python, the list starts at 0. So I've got my linear model is this model here. That's what I've pulled out here. So LM is my linear regression model. And once I have that, then I can do things with it like print out my intercept and use the coefficients to print out the equation. And I can also transform with that fitted model. It has both the vector assembler and the linear regression model. I can transform my data in order to get my actual price and my predicted price. So these are my labeled predictions. And once I have that, I can go ahead and take my labeled predictions, which here, I mean, I could have given it labeled predictions, but I passed in LM results. Doesn't matter. It's going to pull out the prediction column and the price column in order to compute the R squared. And once I have that, the linear regression evaluator, I specify the columns involved in the metric, and then I got my evaluator, which I apply through evaluation to my results above. Okay, so this is one way of running R squared on the results. I can also take those results and convert to pandas as I did before and do a plot of actual versus predicted. Okay, now just to show you can add a few more steps to the pipeline. Just added one more step here just for fun. I've got a standard scaler. So again, the same thing as before. I've got my vector assembler. It's going to take in the columns, all the columns except for price and address. It outputs in this sort of chain or sequence, right? Input are from my data, and these are going to be the columns except for price and address. Outputs of vector features. That vector features is input to the next step in my pipeline. So standard scaler is going to take as input the vector features and output a new column called features. And that's a default by all the models. So output goes to features. It's going to be input to linear regression. You don't have to say input column because it defaults to be features. You could actually specify input column if you wanted to, but you don't have to. And then the label column is going to be price. That's what we're going to use for try to predict. Okay, so we're going to fit that. So once I have this pipeline, then I go ahead and fit that pipeline to my data. And so I'm going to fit it to the training data. So the training data is going to be processed by the vector assembler, the standard scaler, and then the linear regression. And as a result of that, I've got a fitted pipeline or fitted model, it's called here. And I can look at the stages of that fitted pipeline. And you can see that they're just the instantiations of the vector assembler, the standard scaler, and then the linear regression. And you can even see here that it's 5 features. Okay, so that's my pipeline. I can go ahead and now pull out, it's the last element in this list is the linear model. So it's 0, 1, 2. And I'll pull out that model. And once I have that model that's been fitted, I can do things with it like, print out the intercept and R squared and all the rest. This model actually has a summary object which allows you to print out the R squared for that training data set. Of course, the training data set could be a little bit different than the actual test data set. So I take this fitted model and I transform it over the test data set and I get results there. And I can select out of that 2 columns, the price and prediction column. I can also make a regression evaluator, telling it to look at the prediction column and the price column and apply the metric R squared. And once I have that evaluator, then I can apply that evaluator by using evaluate to my results above and to print out R squared. And I only show 2 places here, but the R squared is 0.92, which looks to be about the same as on the training data. Remember, this is on the test data. All right, once I have my test data I've got some label predictions. I can go ahead and pass those to pandas, then plot them, which is shown here. And that's doing multiple regression with a pipeline in PySpark. So next up is just to show one more, simplifying way in which people use regression. They often use an R formula if they're going to use some sort of regression. And you don't need to use the vector similar if you use the R formula. And this can be, and also you can specify more complex formulas with R formula than in vector similar. So just wanted to show that. So everything the same here, but instead of vector assembler, I'm going to use an R formula followed by standard scale and linear regression. The R formula is going to output some vector features which are going to be passed to a standard scaler, and then the standard scaler passes its features to linear regression, and then we do our fit. So if you compare, note that I'm using R formula here. Instead of above, we used vector assembler. In R formula, you get to use the formula found in the statistical language R, and you can express it using that language, which is sort of nice and commonly used. Here with vector assembler, I just have to pass in some columns, and that's the columns that are passed in. So let's look at the R formula down below. So if you look at what our formula looks like, I printed it out here, created it here. It's the price followed, predicted by these columns. And it's pretty much just the columns, but you can have more complex formulas than shown here. All right, so we've got our formula. It is going to be applied to our data set to produce some vector features. That's going to be a dense vector column called vector features. That column, vector features, is passed off to the standard scaler, which then produces a new features column. And by default, the models in Spark are going to take a features column. You might have to fill out some other values. In this case, the labeled column is not necessary to be specified. Once I have that pipeline object, then I can fit that pipeline to my training data, and I get a fitted pipeline or fitted model here. So I'm going to go ahead and pull out the last, which is my last step in the pipeline. That's my linear model, and I can go ahead and print out the usual stuff, and including R squared, and it's about 0.92. I can again take my fitted model and transform it on the test data to get the actual versus predicted on the test data set, and then evaluate that and print that out and get my R squared, as well as print out my actual versus predicted. So that's sort of the long way through the PySpark, starting with just a simple single variable regression, and then using vector assembler, and finally using R formula in a pipeline. And that's a demonstration of how to do linear regression in PySpark. And I hope it works for you.